next lesson is about the volumes of prisms and cylinders and Cavalieri's principle. In this lesson, we'll hit two CCRSM standards, GMD1, which is to give an informal argument for the formulas for the volume of a cylinder, use dissection arguments, Cavalieri's principle, and informal limit arguments, and GMD3, which is to use volume formulas for cylinders to solve problems. Let's get started. Lesson 10 starts off with a problem where we're calculating the volumes of two prisms, a triangular prism and a rectangular prism. And we're first asked to find the area of T prime. Well, T prime is right here. It's a triangle, and we know that the area of a triangle is 1/2 base times height. The base is down here, which is 10, and the height is 3.3. And so the area of T prime is 16.5, and we don't have any units. Units squared. Now R prime is this rectangular region right here. Looks like a square. It's close to a square, but isn't quite a square. And so this area is base times height, like all rectangles. And the base, I'll say it's 4 times, and the height is 4.125. And we also get an area of 16.5 square units. All right. Now, notice that when I find the volume of T prime, that it is the area of the base, which is the same as T prime, the area of the base times the height of 5, which is 82.5 cubic units. Now, I don't have it on my screen, but down below at D, it asks you to find the volume of R, which is a prism, so it's area of the base times the height. The base is again 16.5, the height is again 5, and so the volume of R will also be 82.5 cubic units. Okay, so this is briefly how to find the volume of prisms, but something very interesting happens here that's important for our discussion today. The point is that for any height with these two prisms, at any height, the cross sections of that will have the exact same area. Even though the left is a triangle and the right is a rectangle, at every cross section they will have the exact same area, which means as you add up those layers, as you add up those volumes, then you will have the exact same overall volume, even though the shapes look different. Okay, that's kind of the essence of Cavalieri's principle, which we'll talk more about in this video. We'll next look at figure 1, which has three different figures, three different designs, a red, green, and blue. If you look kind of at this height of H, we have three different lengths here, which look to be very similar. In fact, if I had a ruler, I'd measure them, and I'm pretty sure they would be the exact same. Okay, if you go up higher up, you would see a different, two-dimensional cross-section, which would be again the same. And if you look at all of these, at every single cross-section, at every height here, they have the same intersection with that figure, which means as you add up the red area, you would get the exact same area as the green area and the exact same area as the blue area. So even though they look very different, even though they're not congruent to each other, because the cross sections have the exact same area, or in this case length, as you add up the overall area, you would get the exact same area. And here's an image on the next page, kind of where it's chopped up into little small pieces. And so each of these rectangles would be the exact same, and as you add them up all the way up, you get the exact same area. Okay, and we could think about finding smaller and smaller and smaller rectangles until we have them be so small that it would be the exact same as the overall shape. Okay, now that's again Cavalieri's principle, that if all the cross sections have the exact same area, then the overall area or volume will be the exact same. So down here, there's an example with triangles. And I like this example so much that I built a GeoGebra file that kind of talks about the essence of this idea. All right, here is a triangle where the base is EH, and I don't know exactly what this height is, but for our discussion, to keep it focused and simple, the area has been calculated by GeoGebra to be 12.5. Okay. Now, when I move this point, and I've built this so that this line right here is parallel to EH. As I move this point, what do you think will happen to the area? Well, if I move this point, the area stays 12.5. Okay. And we saw this when we talked about the side splitter theorem. But the reason why the area stays the exact same is even as you move this, the cross sections of this, even as you move it, will stay the exact same as you move it. So these cross sections, no matter how far I stretch it, will still be the same. And by Cavalieri's principle, that's why all these triangles, this triangle, this triangle, this triangle, this triangle, will all have the exact same area. Figure 3 is a three-dimensional version of the figure we saw in Figure 1. And here we have three different prisms or general prisms. On the left, we have a right rectangular prism, and you found volumes of this in the past. It's length, width times height, or the area of the base times the height. In the next figure to the left is what we call an oblique prism, where it's kind of leaning in one direction. Okay, all the way on the right, it's like a curved figure. Okay, but the important thing is that at any height, you'd have the exact same cross-sectional area, and so as you add up those areas and get a volume, you get the exact same volume. Okay, I like to think of this as a stack of cards or like a ream, like a big stack of papers that you can kind of push those to the side, kind of like B or A, I'm sorry, like the second figure or the third figure. You kind of lean those or curve those, and that won't change the volume of the cards or the paper. Okay, because every single sheet of paper, all those will be the exact same, even as you kind of make the stack lean or kind of curve. And down here we have Cavalieri's principle. Given two solids that are included between two parallel planes, if every plane parallel to the two planes intersect both solids in cross sections of equal area, then the volumes of the two solids are equal. That's the idea we've been talking about in this entire video. Okay, so this video is about the volumes of prisms and cylinders. Now I felt that it was not right to finish out this video without reminding you of the formula for the volume of a cylinder. We know that the volume of a prism is the area of the base times the height. We've used that one so far. Now in a cylinder, the base is a circle, which we know is pi r squared. So we could use the formula pi r squared as the area of the base times the height. And I feel like you should get those two formulas in this video if it's about the volumes of prisms and cylinders. Okay, and keep in mind, we'll look at this in next class, that for cylinders or prisms, if they're leaning or curved somehow, but by Cavalieri's principle, if every cross-section is a circle or a rectangle, or that same as the base for the prism, they have the exact same area. So this video was mostly about Cavalieri's principle, but also talking about the volumes of prisms and cylinders. Thank you for watching.